Welcome to Ask and Learn.
Hi there. So for this problem, we are told that monochromatic light is beamed into a Michelson interferometer. So the movable mirror is displayed a distance of 0.382 millimeters, causing the central spot in the interferometer pattern to change from bright to dark and back to bright, with n equals to 1,700 times. So for part A of this problem, we are asked to determine the wavelength of the light and what color is it. So when the central spot in the interferometer pattern goes through a full cycle from bright to dark and back to bright, two fringe shifts have occurred, and the movable mirror has moved a distance that is going to be equal to 2 times the wavelength divided by 4, which is equal to the wavelength divided by 2. Thus, the n, if we have n cycles, these n cycles given, such cycles are observed as the mirror move a distance, this distance right here. It must be true that d, the distance d, is equal to the n cycles times the wavelength divided by 2. Or also, if we solve for the wavelength, we will find that that is 2 times the distance d divided by the number of cycles. And since we know these two values, we just need to simply substitute them in this expression to obtain the wavelength. So we will have that this is 2 times the distance d, which is 0.382 times 10 to the minus 3 meters, and this divided by the n cycles, that is 1,700. So from this we obtain a value of 4.49 times 10 to the minus 7 meters. So this is equal to 449 nanometers. So if we search for this into the spectrum of light, you will find that this corresponds to blue light in the visible spectrum, of course. Now, for part B of this problem, we are asked about if monochromatic red light is used instead and the mirror is moved to the same distance, will n be larger or smaller? Now, red light, um, red light has a longer wavelength, so than blue light, of course. So fewer wavelengths will cover the given displacement. Hence, the n cycles will be smaller. So that's a solution for this problem. Thank you.